Okay, so welcome back to this next video in which we are discussing centralizers and normalizers. Okay, so we've now just defined what the normalizer of a subset capital A in the group capital G is actually going to be equal to, and we've seen that it is actually going to be the subset of the group capital G that contains all elements of the group which when you use that element of the group to conjugate any element of the subset capital A, gives you another element of the subset capital A, and that's true for all elements of that subset capital A. So it's all elements of the group which, when you conjugate the subset capital A by that element, when you conjugate the elements of the subset capital A by that element of the group, it maps it onto another element in that subset capital A, okay? And the claim that I made at the end of the previous video is that the normalizer of the subset capital A in the group capital G is in fact a subgroup of the group capital G, okay? And that's what we want to try and prove now. Okay, so we know that it's a subset of the group capital G, okay? So once again, to prove that it's a subgroup, we need to prove the 4 axioms of group theory, and we don't need to bother with the second one because any subset with the inherited composition law from the larger group on it will actually obey the second axiom of group theory, so we don't need to worry about that one. Okay, so once again, let's start with axiom number 1, which is closure. Okay, so we need to prove that you give me any two elements, let's say little g1 and little g2, from this subset, which is the normalizer of the subset capital A in the group capital G. And we need to prove that the composite of the two, so the two composed together, g1 composed with g2, is also an element of the normalizer of the subset capital A in the group capital G. So we need to prove that it's closed under composition, that if you've got any two elements of the normalizer of A and G, that the two of those composed together is also an element of the normalizer of A in G. Okay, so I should just put a little to show in here. Okay, so we want to show that. Okay, right, so firstly, let's just reduce this into something that we can actually work with by using the definition of being in the normalizer of A in G. Okay, so what this means is that if we conjugate any element of the subset capital A by g1, g2, okay, so we take g1, g2, A, and then we'll have g2 inverse, g1 inverse, which we know is the inverse of g1, g2, we need to show that that is some other element of the set capital A. Okay, and we need to show that for all little a is an element of the set capital A. So this is what we need to show. So I've just used the very definition of this being true, and now we need to show that this is true. Okay, so quite simply, let's consider what you would get if you took some little element of the set capital A. So let's say we take some little a, which is in this set capital A, some arbitrary little a from our set subset capital A, and we are going to consider what is g1, g2, a, g2 inverse, g1 inverse. We're going to consider what actually is this element little a conjugated by g1 composed with g2. Okay, well, what are we going to do here? Well, at some point we're going to need to use the fact that g1 and g2 are elements of the normalizers of A and G. And just like the proof that we followed in the centralizers case, okay, we're going to use that fact round about now. Okay, so what we're going to do is we're going to look at this middle portion here and look at what we've got there. We have got g2a, g2 inverse. So we've got the conjugate of A by this element g2. Now we know that g2 is an element of the normalizer of A in G. Okay, so we know that whatever this answer is, it's going to be some element in the set capital A. So let's call it A bar. Okay, so whatever this is, it's some element of the set capital A. Let's call it A bar. Okay, so what we can now do is rewrite this as g1 A bar, g1 inverse, where all we know about A bar is that it's some element of the set capital A. Okay, now what we're going to do is use the fact that g1 is an element of the normalizer of A and G, because now what we're doing is conjugating A bar by this element g1 A bar is an element of the set capital A, so whatever the answer to this is, this has to be another element in the set capital A. Let's call it A double bar. Okay, and that's quite simply because when you conjugate any element of the set capital A by G1, it has to give you another element of the set, because that's the definition of G1 being in the normalizer of A in G. Okay, so this also has to be another element in the set capital A. Okay, so we've just taken G1, G2, A, G2 inverse, G1 inverse, the conjugate of A by G1, G2, and we've reduced it into this A double bar, which is an element of capital A. So I've just proven that this conjugate of this element little a from the set capital A by G1 composed with G2 is another element of the set capital A, basically. Okay, so that then has done exactly what I needed to do. It has proven that if G1 and G2 are elements of the normalizer of A in G, then G1 composed with G2 is also going to be an element of the normalizer of A in G. Okay, so it is closed under composition, basically. Okay, so axiom number 1 of group theory is now complete. Okay, so now let's move on to axiom number 3 of group theory. Okay, so axiom number 3 says that this normalizer of A in G needs to have an identity element if it's actually going to be a subgroup of capital G. Okay, now that means that it needs to contain the identity element from the original group, capital G, but we've already noted that it had to contain the identity element from our original group because it actually contained all the elements of the centralizer of A in G, and the centralizer of A in G contained the identity element. So we already know then that the identity element is indeed an element of the normalizer of A in G. And the way you can just affirm that in your head is that if you conjugate any element of the subset capital A by the identity element, you will just get the same element of the subset back again. Okay, and that certainly sends all of the elements of the subset capital A onto themselves, okay? Well, onto an element of the set capital A, and therefore it meets the requirement to be in the normalizer of A in G. Okay, right, now what we're going to do is the most complicated one, okay, showing that inverses are in this set. Okay, so this is going to be the most tricky, okay, and this is going to require us to delve a little bit deeper into conjugation on this set capital A. Okay, so axiom number 4 then of group theory. So what we need to show is that if you take an arbitrary element of the normalizer of A in G, okay, so let's take an arbitrary little g which is in the normalizer of A in G, okay, what I need to show is that, and I'll put this, to show that G inverse, which I know is another element of the group capital G, is also an element of the normalizer of A in G. Okay, and let's apply the very definition of being in the normalizer of A in G, and let's see what we need to prove then. So we need to show, so this is equivalent to showing that G inverse A G, okay, so the G inverse conjugate of any element little a, whatever this is, it needs to be another element of the set capital A, okay, and that needs to be true no matter what little a you pick from the set capital A. So we need to prove that G inverse will conjugate this element little a to give another element of my subset capital A, okay, and what we know is that little g is an element of the normalizer of A in G. So little g can conjugate any element of the subset capital A to give back another element of the subset capital A. Okay, so how are we going to do this? Well, you remember when we were showing that the centralizer of A in G was a subgroup of capital G? We applied a very nice, clever trick there. What we were able to do is we were able to substitute in for A there, we were able to substitute in GA, G inverse. We were able to say because G is an element of the centralizer of A and G, it's true that GA, G inverse gives you little a, no matter what little a you're talking about in this subset capital A. So we were able to stick that in for little a here, and then the G inverse was able to cancel with the G, and the G inverse here was able to cancel with the G there. Okay, and that was what made it so beautiful. Here it's a little bit more complicated, okay, but we're going to try and do the same thing. So what I would like to do is replace little a here with something of the form little g, little a bar, little g inverse. Okay, for some, little a bar is an element of capital A, so let's appreciate exactly what I'm saying here. If I could write little a in this form, okay, so if I could prove that I would be able to write little a in this form, where I'm conjugating some other element of this set capital A, and I'm calling this other element little a bar, by the element little g, okay, to get little a, if I could write little a in this form, then what I could just do is substitute this in here, and then again my little g inverse could cancel with my little g inverse here could cancel with my little g here, and I'd then get that the answer to g inverse ag would just be equal to a bar here, basically. Okay, and of course that would be an element of the set capital A. So if I could do this for all elements little a of the set capital A, then I'd be in business, basically. I'd be able to show this. And this is just a generalization of what we were doing in the case of the centralizer of A and G. Okay, so what I need to prove then is that that's the case. Okay, so how am I going to do that? How can I prove that there will always be a little a bar such that I can write little a as the little g conjugate of little a bar? Okay, well, this comes from the fact that conjugation represents a set permutation of this set capital A. Okay, so we're going to take a step back and we're going to study this normalizer of A in G in a little bit more detail. Okay, so basically if you have some element little g from the normalizer of this set A in the group G, you can use this to associate with the element little g a set permutation of the set capital A. Okay, so what I mean by this is if we have this subset capital A, okay, so here is our subset capital A, and I know this is a subset of our group capital G, but I've now pulled it out of the group capital G and it exists now in its own right. So here is my subset capital A. Okay, and I'm going to need another copy of it because we're going to be thinking about set permutations of this set capital A. Okay, so here is another copy of capital A here, and again I'll colour that in green here. Basically what you can do is you can think about taking all the elements of the normalizer of A in G and associating them with set permutations of the set capital A. So for little g, you can associate it with a set permutation which we'll call sigma little g, okay, which will map the set capital A onto itself. Okay, so it'll be a mapping from the set capital A to itself, and the way that this will work is that sigma subscript little g will map any element little a of this set capital A, so I'll map any little a here onto GA, G inverse, so the G conjugate of that element little a. Okay, so it's going to be mapping all elements of my set capital A onto another element in the set capital A, and of course we know that it will be a mapping from the set A onto the set A because that's the very definition of these elements being in the normalizer of A and G, that whenever you conjugate any element of the set capital A by that element little g, it gives you another element in the set capital A, okay, not something that's outside of capital A. Okay, so I'll just complete this picture by putting GA, G inverse there. Okay, right. So what I want to show you is that this is more than just a mapping from the set capital A to the set capital A. It's actually a bijective mapping. It's a set permutation of the set capital A, and this is true no matter what little g you pick from the normalizer of A and G. Okay, so how do you show then that a mapping is a bijection? Well, the way that you show it is that that mapping has a two-sided inverse, okay? Because if it has a two-sided inverse, that then proves that it is both injective and surjective, and therefore that it's bijective. Okay, so what then is going to be the inverse map of sigma g? Well, I claim it's going to be the map that's associated with the element little g inverse. Okay, and I know I haven't yet shown that little g inverse is an element of the normalizer of A in G. Okay, but this is certainly defined on the larger group capital G. Okay, and it will map all the elements of this set capital A onto some other element in the group capital G. Okay, and what we're actually going to find out is that this actually does map the set A onto the set A and is an element of the normalizer of A and G. But for now, just think of it as sending all the elements of the group capital G onto the G inverse conjugate of them. Okay, so it will certainly act on all of the elements of the set capital A, and it will send them onto G inverse A G here, so the G inverse conjugate of little a. Okay, now I claim that this map, sigma G inverse, is the two-sided inverse of sigma G. Okay, so what I claim then is that if I consider sigma G inverse of sigma G of A, okay, it's going to be equal to little a for all little a is an element of the set capital A. Okay, and I claim also the other way around that if I consider sigma G of sigma G inverse of little a, that's going to be equal to little a for all little a is an element of the set capital A. That's what it means for sigma G inverse to be the two-sided inverse of this mapping sigma G, basically. It means that I can do these two mappings one after each other in either order. So in this case I'm doing sigma G first, then I'm doing sigma G inverse, and overall they give me the identity map, and that means that they have to map little a onto itself for all little a is an element of the set capital A. Okay? Or I can do it the other way around, so I can do sigma G inverse first and then sigma G, and again that has to give me the identity map for all elements of the set capital A. So if I prove these two things, that will prove that sigma G has a two-sided inverse, and having a two-sided inverse, it's a theorem from set theory that we prove in the video on group actions, I believe, that if you have a two-sided inverse, that means that the mapping must be bijective. Okay, right, so let's prove that this is the case. So firstly, let's do number one. Okay, so if we consider sigma G inverse of sigma G of A, so we're firstly doing sigma G of A, so we can replace that with GA G inverse, okay, just replacing it with what it is. Then doing sigma G inverse of this answer, we'll have G inverse GA G inverse G. Okay, so we'll now be conjugating this answer by G inverse, okay, and clearly you can see that is actually just going to give us A for whatever little a that you have in the set capital A. Okay, because of associativity we can reassociate the elements here, change the brackets here, okay, and we'll get that the G inverse will cancel with the G here and the G inverse will cancel with the G here to just leave little a here. Okay, so that's the top one, and the bottom one follows the same sort of proof. Okay, so sigma G inverse of A, we can replace that with G inverse A G, and then sigma G of this answer, we can do G and G inverse here. So we're going to conjugate this answer by the element little g. Okay, and again what we can do is just change the brackets here, put the brackets around the G and the G inverse here and the G and the G inverse here. Those will both become the identity element, and this will again become little a no matter what little a you were working with. Okay, so what I've shown you then is that this mapping, sigma G inverse, is in fact the two-sided inverse of sigma G. Okay, so what that then means is that sigma G is a bijective map from the set A to the set A, okay, and therefore it represents a set permutation of the set capital A. Okay, so conjugation as a map from the set A to the set A is a bijective one. Specifically, that means that it's a surjective map. So if I take an element little a here, if I take the element little a here, there will be some element back in the domain of the map here that was mapped onto it by conjugation, and we'll call that element little a bar. So there is some little a bar such that when I conjugate it by this element little g, it gives me a little a. So all of this, all of what we've just done was in aid of proving that for whatever little a you have within the set capital A, there is some little a bar over here which when you conjugate it by little g gives you little a. That's what all of this was in aid of trying to do. Okay, all we were trying to prove is that this little a bar actually exists. So basically, I've lost it back here. What I have just shown you, is this the right thing that I want? Yes. Okay, what I have just shown you is that yes, we can do this. No matter what little a you're considering here, you can always rewrite it in this form. You can always find a little a bar in the set capital A such that when you conjugate it by little g, it gives you little a. So now what I'm going to do is use this, rewrite little a in this form, and insert it in here. So if I'm trying to work out what is g inverse of g inverse composed with little a, composed with little g, the g inverse conjugate of little a, I'm now just going to insert in little a is equal to g a bar g inverse, the g conjugate of some element little a bar. Okay, and whoops, get rid of that bit. Now what I can do is just cancel the g inverse and the g here, and the g inverse and the g here, and get that the answer to what the g inverse conjugate of this element little a is equal to is little a bar here. Okay, so this element that you could conjugate by little g to get the element little a. Okay, and little a bar is some element of the set capital A. So I have just proven for an arbitrary little a in this set capital A, if I conjugate it by the element little g inverse, it will be another element in that set capital A. Okay, and therefore I have proven that if little g is an element of the normalizer of A in G, then little g inverse will also be an element of the normalizer of A in G, and therefore that the normalizer of A in G actually does obey the fourth axiom of group theory, and that's the fourth and final one. So the normalizer of A in G, no matter what subset capital A we pick, is a subgroup of the group capital G. Okay, right. So one final comment on the normalizer of a subset capital A in the group capital G. Okay, and this relates to the what if you have a special subset capital A of the group capital G that happens to be a subgroup of capital G. And this is really going to explain why the normalizer of a subset capital A in a group capital G is actually called the normalizer of capital A in capital G. Okay, so let's draw the picture here. So we'll have our group capital G here. Okay, and now what we'll have is our subset capital A here, which is actually more than just a subset. It's a subgroup of capital G. Okay, so I'll colour capital A there in blue, and then we'll have the entire group capital G here in turquoise. Okay, right. So now let's consider what the normalizer of A in G is actually going to be in this case. Okay, well the first thing that I want to talk about the normalizer of A and G in this case is that actually capital A is going to be completely contained within the normalizer of A and G. All the elements of the set capital A itself are going to be within the normalizer of A and G. Now why is this the case? Well, quite simply, they satisfy the condition that is needed to be in the normalizer of A and G. And let me just write out once more what that condition was actually equal to. So remember, the condition that you had to obey to be in the normalizer of A and G is it had to be the case that if you conjugate any element of the subset capital A, okay, you have to give some other element of the set capital A. So what for all little a is an element of capital A, this condition must be true on your little g if little g is to be an element of the normalizer of A in G. Okay, now if little g is an element of the subset capital A, then quite simply we will be looking at a composition of 3 elements that are all in this subgroup capital A. Now, subgroups need to be closed under composition, so if little g here is an element of capital A, little g inverse has to also be an element of capital A because it's a subgroup, and then we'll be composing 3 elements in the subgroup capital A together, and that, whatever it is, has to be another element of the subgroup capital A because of closure under composition in a subgroup. So it must be true then that if you conjugate one element of the subgroup capital A by another element of the subgroup, that you get another element in the subgroup. Okay, so that means that all of the elements of the subgroup capital A itself would actually end up being in the normalizer of A in G, if this subset capital A happens to be a subgroup. That is not necessarily true if A is just a general subset of capital G, because if it's just a general subset of capital G, then closure under composition doesn't have to be true for that subset. Okay, right. So, next big thing then, what I actually claim is that this subgroup capital A will be contained within the normalizer of A in G. So I'll just draw that on. That's the thing that I've just proven. But what I want to show you now is that actually it's going to be a subgroup of the normalizer of A and G, and it's actually going to be a normal subgroup, which is why the normalizer of A and G is actually called the normalizer of A and G. So the normalizer of A and G contains the subgroup capital A, but it might contain elements in the group capital G that are outside of the subgroup capital A, which is why I've shown it being slightly bigger than the subgroup capital A here. Okay, what we know is that the normalizer of A in G is actually a subgroup in its own right, so it's a group. So what we can say is actually capital A is a subgroup of the normalizer of A in G. Okay, because if it's a subgroup of capital G and it's completely contained within this other group, the normalizer of A in G, then it certainly is then going to be a subgroup of the normalizer of A in G. Okay. But in fact it's going to be more than just any old subgroup of the normalizer of A and G. It's actually going to be the case that A is a normal subgroup of the normalizer of A and G. Now why is that the case? Well, what is the definition of a normal subgroup? Okay, so just going over the definition of a normal subgroup, if we have more generally N, which is a normal subgroup of capital G, what that means is that for all little g that you can take from the group capital G, and for all little n that you can take from the normal subgroup capital N, it must be the case that if you conjugate the element of the normal subgroup by the element of the group, you end up with another element of the normal subgroup. Okay, so just drawing this on, if we've got our group here and our normal subgroup here, and I'll colour them in. Okay, so we'll have our group here in vivid purple, okay, and we'll have our normal subgroup here in green. Okay, so you pick any element of the normal subgroup and conjugate it by any element of the group capital G. Whatever you get, it must be another element in the normal subgroup N. That's the definition of a subgroup being a normal subgroup. So why is this capital A, which is a subgroup of the normalizer of A and G, actually a normal subgroup? Well, what do we know? We know that if we pick any element of the normalizer of A and G, okay, so pick any little g is an element of the normalizer of A and G, and conjugate an element of little a by that element of the normalizer of A and G, so pick any little a you like from the subgroup capital A, we know by the very definition of the normalizer of A and G that this must be an element of the set capital A. Okay, so this meets the exact criterion for being a normal subgroup, which is that any element of the larger group, which in this case is the normalizer of A and G, conjugates any element of the subgroup capital A to give another element of that subgroup capital A back again. So this is why the normalizer of A and G is actually called the normalizer of A and G, because if A is actually a subgroup of the group capital G rather than just some arbitrary subset, then when you construct the normalizer of A and G, it will be a bigger subgroup of the group capital G that completely contains the subgroup capital A, and if you view capital A as being a subgroup of the normalizer of A and G, which indeed you can do, it will actually be a normal subgroup of the normalizer of A and G. So what I'm saying is basically get rid of the rest of G. Just now imagine the normalizer of A and G as being a group in its own right. Get rid of that. Okay, then the subset capital A, which is a subset of the normalizer of A and G, is going to be a subgroup inside of that. Okay, you can quite easily check that it will still obey all of the axioms of group theory inside of the normalizer of A and G. Okay, and in fact it will end up being a normal subgroup of the normalizer of A and G, because if you conjugate any element of this subgroup capital A by any element of the normalizer of A and G, it gives you an element back in that subset capital A, okay, by the very definition of the normalizer of A and G. So this is the largest subgroup of capital G that contains the subgroup capital A, in which this subgroup capital A will be a normal subgroup, basically. So it's what you can imagine having the subgroup capital A contained in if you want capital A to be a normal subgroup. Again, that's the motivation for why it's called the normalizer of A and G. Okay, and with that we will end this introductory video on centralizers and normalizers.